Kia ora koutou, no mai, haere mai. Welcome to lesson 11 for introductory physics. This lesson is going to, in a way, go right back to where we started. We're going to look at motion again, but this time we're going to look at circular motion. Everything we've done so far has been linear, straight lines. Even if we could decompose it into two parts, like projectile motion, it was still linear within each part of that motion. So what we're going to do instead is now look at things where we can't break it down into linear motion components, and we instead have to consider the motion of something traveling in a circle as a whole. So the goals are to define the properties of circular motion, the same way we defined properties of regular motion or linear motion. But then we're going to meet centripetal acceleration and centripetal force, which are what are responsible for circular motion. There's a bunch of properties there we'll be defining: period, path radius, angular speed, tangential speed. And then we'll introduce centrifugal force, which is something many people have heard of, but there's a lot of confusion around what that actually means. Finally, we're just going to introduce a couple of concepts called center of mass and torques. Center of mass and torques. I said that a bit weird because I was about to say calculate and then I changed to center. So let's get going. We're going to first of all think about the types of circular motion that we're going to discuss. Firstly, as I already said, everything we've done so far has been linear, even projectile motion that we've been able to break down into two components. We had one, the horizontal component, that just had a constant velocity, and then we had the vertical component that had a constant acceleration of 9.8 meters per second downwards. So we could easily break it down, and then it was just a linear motion problem. And linear motion problems are what we've been doing so far. Everything we've done has been a linear motion problem. So that's nice and simple. When you get a net force, the direction of the force is the direction of the acceleration, and that's the direction of the velocity, and everything's nice and constant. So that was easy. But now we're going to think about when we have non-linear motion. So non-linear simply means that the direction of the force or acceleration is changing. So in linear motion, we already met the concept of the acceleration or net force being different to the initial velocity. That's what projectile motion is. Projectile motion is you've got a horizontal velocity and then you get a vertical acceleration, or you might even have projectile motion at any angle. It might start at being launched at an angle, not just horizontal, any angle, but the acceleration was always straight downwards. It was always one direction for the net force. Non-linear motion is when that direction of the net force changes throughout the motion. That's all it means. So linear motion, the net force is in one direction all the time. Non-linear motion, the net force changes direction over time. In reality, of course, purely linear motion is not that common because there are lots of other forces that we sort of ignore or assume are negligible. And again, those implicit assumptions that we make mean that we can treat many scenarios as linear motion, and it works perfectly fine within our tolerances, within our precision. But there are obviously certain circumstances where we can't treat it as linear motion. The first type of non-linear motion we're going to look at will be the idea of an object traveling along a circular path. The simplest example is a planet orbiting a star, but there are a lot of other examples: a car going around a corner. If it's a perfectly circular corner, for example, the car travels around that. That is a circular path, even if it doesn't do a complete circle. The next one is rotation about a fixed point. So this is where you've got something that has an axle or some kind of way that it's attached to a certain location about which it can rotate. So that location is stuck in space, and that part of the object that is attached to it. So for example, the center of a car wheel onto the axle, that is stuck on that exact location. The center cannot move away from that axle, but the wheel itself can rotate about that point. And a merry-go-round, the whole merry-go-round, not the people on it, the whole merry-go-round is attached to an axle in the very center, and it spins around that axle. So it's rotating about a fixed point. And then the last thing that we'll talk about is the concept of an object rotating about itself without some fixed axis of rotation. So this is what would occur if you spin a ball as you throw it, as per the GIF there. If you spin that ball and throw it, it will rotate as it travels through the air. It doesn't have to be traveling through the air. It might just be spinning on the spot. You might just have it on a frictionless surface and start it spinning. And so we're going to talk about what happens when something spins or rotates without having a fixed axis. So to start with, those circular paths, as I said, we're going to go right back to the start and we're going to define our motion. In order to make sense of it all though, we want to return to acceleration as a vector. This is something we almost skipped over a little bit. I didn't get too graphic with my acceleration vector example, so I'm going to do that now. When you have an acceleration vector, that is how much the velocity vector changes every second. And we know that you can just add vectors together by putting one at the end of the other. So here we've got the purple vector. On the left is our velocity at a certain time. The green vector is our acceleration, and that is constant. We've got a constant acceleration of 1 meter per second. And at time t equals 0, we start with a velocity of 2 meters per second. So that means we take our 2 meter per second velocity and we add on the acceleration vector, and that tells us how big the velocity vector will be for the next second, right? 1 second later after that acceleration has occurred, and so on. And you can just keep adding that acceleration vector on every second, and it shows you what the velocity vector will be every second. And so that's pretty straightforward, because all we're saying is that the direction's not changing, the velocity is just getting 1 meter per second longer every second. But if the acceleration direction isn't the same, then we're not just going to change the magnitude of the velocity, we're going to change the direction. In that previous example, and in most of the examples we've seen so far in the course, we've talked about acceleration and velocity in one direction. Projectile motion, we would break it down, but we'd still just consider the velocity in that vertical direction and the acceleration in that direction. And whether it's opposing the velocity or in the same direction as the velocity, we get that change in magnitude, but not direction. Obviously, with projectile motion, we did get a change in direction, but we could still break it down and simplify it to linear. But if the acceleration direction is different to the velocity direction, the velocity will change direction over time. And so that's, as I was saying, that's what we saw with projectile motion, but we can't make that simple an explanation of circular motion. Let's just think about that a bit more. If you have a car, this is a little toy car traveling forward with that small black velocity vector, and we add a force to it. We apply a force to try and change the car's velocity. That top picture, if we just push in the same direction as that velocity, it is going to increase the magnitude but not change the direction. That's the simplest linear motion. If we push at an angle, so that our acceleration is at an angle relative to the velocity, then that's going to change both the magnitude and the direction of the velocity vector. But if we think about pushing exactly perpendicular to the car's velocity, then it's not going to change the velocity magnitude at all. It's not going to change the speed of the car. It's just going to change the direction. We're basically just shoving the car sideways. It'll still keep going with its same velocity that it had, but it will now be pointing in a different direction. So we get no change in speed, just a change in direction. And that's still an acceleration, because remember, an acceleration can be either a change in speed or a change in direction. And if you change the direction of that force, of that acceleration, so that it's always perpendicular to the velocity, then what you get is the magnitude or the speed never changing, and you just get change in direction. And that's what a circular path is. So a circular path is just a constant speed, so a constant magnitude of velocity, but with a perpendicular acceleration that is always being applied, so that the direction of the velocity is just constantly changing. And you can imagine, hopefully, if you picture that, that diagram I've got there, if you increased the magnitude of that acceleration, then it would curve more sharply. So if you have a bigger acceleration, it's still not going to change the magnitude of the velocity, but it would make the circle smaller. It would make the tighter curve. So that's what perpendicular acceleration will do. That's how we cause circular motion. We apply a constant perpendicular acceleration to the object. So an acceleration that is constantly perpendicular, it always points towards the center. So I'll go back a slide actually and just point that out. If you look at those acceleration vectors, those little green vectors, you can imagine that if you continued them all, continue the line of those acceleration vectors, they're all going to meet right in the middle of the circle that would be traced out by these vectors, by the velocity vectors. So the acceleration being perpendicular means the velocity will make a circle and the acceleration will point to the center of that circle. And for that reason, we call it centripetal acceleration. Centripetal just means center seeking. That's all it means. It points towards the center. Of course, accelerations are caused by forces. So we need a force that will cause this acceleration, and that is just the centripetal force. How big the perpendicular acceleration is determines how quickly the object turns. This is, as I was saying, if you imagine the acceleration getting bigger, the turn will become sharper, the circle will get smaller. We're going to define the properties of circular motion, then we're going to come back to centripetal acceleration. So keep this in mind. We will end up back at this point and we'll get a formula for it in terms of the other properties of our circular motion. Some examples though, we've got the Earth orbiting the Sun. Gravity is the centripetal force. Car driving around a circular corner at a constant speed. We have friction between tires and the road as the centripetal force. I want you to visualize these scenarios and try and picture this force that's acting on the object towards the center of its circular path. And the last one, swinging an object tied on a string. The tension from the string itself is the centripetal force on the object. So everything we've done so far has been for linear motion, as I've said. What properties do we need to know for circular motion? Because it's not going to be exactly the same. We're going to follow a similar process, but it's not going to be exactly the same. The most important ones are going to be, where is the center of our circular path? How frequently does the object go around the circle? How quickly does it do one revolution? And what is the linear speed as it travels around the path? So while it's traveling around that circular path, the velocity is constantly changing, but we see the magnitude of the velocity, which is the speed, is constant. So what is that speed as this object is traveling around the circle? Those are sort of, you can hopefully imagine those are the pretty obvious properties that we'll want to define. So the first one, the path radius, that is the distance from the center of the path to the path the object is traveling on. That is a distance, so it's going to be in meters. Its dimension is going to be a length, so any distance units are fine, but again, the SI unit is meters. The symbol does vary. You may have multiple objects on multiple paths, and you may use different letters or different symbols to indicate them, but the most common ones are R, just the letter R, or a capital letter R. Some examples, the Earth around the Sun has radius of 149 million kilometers, or 150 million kilometers. The Moon orbiting the Earth has a radius of 384,000 kilometers. And a child around a merry-go-round, it will depend on the size of the merry-go-round, but I'm going to just come up with a few values because I'll keep these three examples going through each of the properties that we're looking at. So we're going to imagine a 2-meter radius carousel. Notice that this is different from when I mentioned a merry-go-round as being something rotating about a fixed axis. And this is the reason I've included this child on a merry-go-round as an example, is because you have to distinguish whether you are thinking about the object that is rotating. In this case, the merry-go-round itself is rotating about a fixed axis. So the whole object is rotating around that fixed axis, or something attached to it, such as a child sitting on one of the seats, that is being transported in a circular path. So that a child is not rotating about that fixed point in the same way that the merry-go-round is. The child is being rotated around a circular path, whereas the merry-go-round itself stays in one location but rotates on the spot. So there's that slight distinction, which is why I've included both examples. The path length is simply the length of the path that the object travels to complete one full circle. We're all familiar with circles. Circle, the path length is going to be the circumference, and that is just 2 pi r. R is the path radius that we just defined. So again, it's a distance, so we've got SI units of meters, dimension of L, and there is no specific symbol. You can, if you want, go back to the idea of D or X for distance, but generally we're just going to write 2 pi r because we know it's the circumference of the circle, and 2 pi r is pretty simple to write. The examples there, the same three, as I said, I'll keep them going. We've got Earth around the Sun. Its path distance is 9.4 times 10 to the 11 meters. The Moon around the Earth is 2.4 times 10 to the 9 meters. And that child on the 2-meter radius merry-go-round will have a path length of 12.6 meters. Do feel free to verify those. I may well have not got them correct, but do have a go at checking those yourself. It's a simple calculation, 2 pi r, but it is a good chance to check your unit conversions because the previous values were in kilometers for the Sun and Earth orbits. The next bit of information is the period. The period is the time taken to complete one full revolution. So travel from one point on that path all the way around the path back to where you started. So one path length. It's a time, so the SI units are seconds, dimension is T, any time units are acceptable, and the symbol we use is capital T. That's a very common symbol for period, so do stick to that one. We will need it again when we look at simple harmonic motion or oscillations, vibrations later on in the course. So period is capital T. Examples, the Earth going around the Sun, we have a period of 1 year. The Earth takes 1 year to do a complete rotation around the Sun. That is 3.15 times 10 to the 7 seconds. Practicing unit conversions there. Moon around the Earth, it orbits the Earth once every 27.3 days, which is 2.36 times 10 to the 6 seconds. And that child around the merry-go-round, again, it depends on the carousel, on the exact setup of that merry-go-round. We are going to make a guess and say that this child has a period of 6 seconds. Remember that we get to define our frame of reference however we like. For a lot of the examples so far, or pretty much all of them, we've chosen an X and a Y axis, or possibly just an X if it was one-dimensional linear motion. So for linear motion, having nice linear perpendicular axis dimensions, whatever you want to call them, is fine. It makes sense, especially when gravity is one of the forces acting, or a normal force is the obvious force for the vertical, or whatever you want to do. That all makes sense. But for circular motion, that's not very useful, because the object is constantly traveling in both dimensions, and trying to break everything down into fit our X and Y coordinates would actually be really mathematically quite messy. But what we could do, and we've already briefly mentioned this when I was talking about frames of reference, is the idea of measuring that radius, because that's not going to change, and then just measuring the angle relative to some fixed point. So I've drawn a little diagram there. You can see I've chosen some direction. I've chosen to the right, in my case, to be my fixed line of reference. Doesn't actually matter where you put that, but that fixed line of reference, and then you measure your angle relative to that fixed line. So you can see that that one is up at around about 45 degrees, probably slightly over, maybe 50 degrees from that horizontal reference line that I've chosen. And so in that way, I'm still using two dimensions to reference where this object is, but I'm using a radius and an angle instead of two different displacements, instead of an X and a Y. I could say that it's across X and up Y and use trigonometry to figure out what X and Y are here, but then as soon as that object moves, both X and Y are going to change, and I'd have to go and recalculate them. But if I instead use my radius and my angle, then as soon as the object moves, that radius is not changing. Simple, I can just say it's always R, and theta, the angle, is the thing that's changing, and I can just tell you how much that's changed. And it's much easier to convey that circular motion using this sort of frame of reference. So whenever we're doing circular motion, this should be your default thought for a frame of reference. That's not to say you'll always have to use this exact setup, but it should be your default starting point, just like a default X and Y is your default starting point for a linear system or scenario. I will just take a moment to talk about angles. Most people are familiar with degrees, but not everyone is familiar with radians. Radians are the angle that we will generally use. They are the SI derived unit for angle. They're not really an SI unit in the same sense, because angles are technically dimensionless. Angles don't actually have a dimension. That means we don't need to include them in our dimensional analysis. There's no symbol for them for our dimensional analysis. But you do need to remember that they do have a unit, and make sure you're clear about whether people are talking degrees or radians. Symbol for angle is just theta. That's the default symbol. Again, you can use other symbols, but when we're talking about circular motion, theta is the standard symbol. So do try and stick to that one. 1 radian is defined as the angle which subtends an arc of length equal to its radius. So if we've said that circle has a radius of r, then if you trace out one length r along the circle, the point that you end up at is an angle theta away from where you started. So using our frame of reference of r and theta, the theta would change by 1 radian if your path length was just r. So that's what a radian is. That's how it's defined. And there are 2 pi radians in a full circle, which is where we get our formula for circumference from, 2 pi r. Because if you have to go around 2 pi radians, then that means each radian is adding r to your path length. So you just have 2 pi r as your path length. So 2 pi radians in a full circle, we have 1 radian will create an arc of length r. You do want to be able to convert between radians and degrees. I haven't got that information in the lecture here in the lesson notes, but do try and figure that out or Google it or whatever. I might actually, I'll just jump over and I will write it quickly on my document camera. But essentially, if you have to do 360 degrees, and that's equal to 2 pi radians, then hopefully you can realize that to change any angle, you're just going to figure out how much of a full rotation it is. So if you've got x degrees, then you want to divide it by 360 degrees, and that'll tell you how much of a full rotation you have, and then you just multiply it by 2 pi. And that will give you your angle in radians, y radians. So that's always true. Whatever your angle is, if it's in degrees, just divide it by 360 and times by 2 pi, and that will give you your angle in radians. Conversely, you can divide by 2 pi and multiply by 360 to go from radians back to degrees. So I'm not going to go any further into that, but do spend a bit of time just reading up on that if you're not confident in moving between angles and radians. And the other thing I'll mention at this point is to check your calculator and check that you know how to convert between radians and degrees. Most of the time that we deal with angles in trigonometry, we'll be using degrees. When we're doing this sort of circular motion, we are talking about radians, but we don't often actually have to do trigonometry on it because it's just a position. It's not, we're not using it to figure out some other distance. The next thing we want to define is rotational or angular speed. How much the angle in our reference frame changes per second. So velocity or speed, when we're talking linear, was just how much that displacement or distance changes every second. Rotational speed is just how much the angle changes per second. Because I just said before, if I tell you it's some radius r and then some angle theta away from my fixed reference line, and that theta changes by some amount, that's all you need to know for where that object is now. So if I just tell you that that angle is changing by 5 degrees every second, or half a radian every second, or some other value every second, you know exactly what the motion of that object looks like. The angle is changing by that amount every second. So that's nice and straightforward. Because it's talking about the angle changing, technically, rotational speed and angular speed both mean the same thing. I prefer to use angular speed because it's just a really good reminder that what we're talking about is the change of the angle. We're not talking about some property of the whole system rotating. We're just saying here's an angle, here's its change, right? So it is a property of the system. But just saying angular speed hopefully will reinforce that it's just the angle we're talking about, nothing else. Because it's an angle change per second, it's going to have units of radians per second. Since angles are dimensionless, we don't have to worry about the radians when we do our dimensional analysis. We just have per second, so t to the -1. The symbol we use is that curvy W looking thing. That's actually another Greek letter called omega, but it's just a curvy W. So if you write your W's normally like that, and you want to distinguish them, I'll just jump back to the document camera just to show you. Normally, a lot of people write pointy W's and curvy omegas, but what you'll see is I just did a little tick, a little flick off the end of my omega, right? Whether you do a little curvy one or a straight one. But if you normally write your W's sort of curvy, then adding this little tick off the end will help you identify that omega. And that's something that I personally tend to do, is write my omegas with this little flick off the end. But you don't have to. It's just another useful trick for keeping all the symbols in mind. The examples, we already met the Earth around the Sun. Oh, actually, I guess I should mention that second bullet point there, the formula for the angular speed. Remember that the period we said was the time taken to do one full rotation. And we said that one full rotation is 2 pi radians. That's what a full rotation is. A full circle, 360 degrees, is defined as 2 pi radians. So if it takes t seconds, period seconds, to do that full rotation, then the angular speed is going to be 2 pi over the period, 2 pi over t. So that's a pretty straightforward calculation. The Earth around the Sun, omega is 2 times 10 to the negative 7 radians per second. For the Moon around the Earth, it's 2.7 times 10 to the negative 6 radians per second. So you can see those are tiny, tiny angular speeds. Because it takes so long, it takes a full year for the Earth to go all the way around the Sun, the angle is obviously going to be changing pretty slowly. For the child on the merry-go-round, though, we said that it takes 6 seconds to go around a full circle. So 2 pi over t is going to give us 1 radian per second. So the angular speed of the child on the merry-go-round that we've made up is 1 radian per second. In general, angular speed can be defined for any system that has a change in angle, and it's the similar formula to what we saw for velocity, which was the rate of change of position over time. Here it's the rate of change of angle over time. So omega is delta theta over delta t. That should be a lowercase t there, apologies. That should be over delta t, lowercase t for time. For instantaneous angular speed, you may remember we don't use these formulas, but those of you with a maths background will be happy to see partial, just derivatives, not partial yet. Derivatives, we've got d theta by dt, the rate of change of theta with respect to time. So that is the formula, but generally we're not going to go into too much detail on circular motion, so just remembering 2 pi over the period is going to be enough for this course. Linear or tangential speed, so this is what we're saying, that while the object is traveling around that path, yes, the angle is changing every second, but it also has a constant speed as it travels. The velocity direction is constantly changing, but the magnitude of the velocity and thus the speed is constant. So what is that going to be? Well, it's a speed. So it's speed, we've got meters per second, dimension L, t to the negative 1, symbol v. That's all the same as we saw for linear motion. We've just got a speed. But speed only depends on the distance traveled and the time taken. We already said the path length was 2 pi r, and the time taken to travel that path was the period. So the speed is just going to be 2 pi r divided by t. That's all it is, the path length over the time taken to travel the path. That's nice and straightforward, hopefully. But we can actually simplify that a little, well, not simplify, but rewrite that a little. We had that the angular speed, omega, was equal to 2 pi over t, and you'll see in that that speed formula, we have 2 pi r over t, so we can replace 2 pi over t with omega. And so it turns out that the tangential speed, v, is equal to r omega. The radius times that angular speed. It's actually a really simple formula. The radius times the angular speed gives us that tangential speed. So some examples again. The Earth around the Sun, that is traveling with a tangential speed of 30,000 meters per second. The Moon around the Earth is traveling with a speed of 1,000 meters per second. And that child that we had on our merry-go-round is traveling with a tangential speed of 2.1 meters per second. From our formula, we can see that there's some simple relationships that we can observe, and that is that if we increase the radius, then the tangential speed will increase as well. So if we keep the angular speed, if we keep omega constant, but we increase r, then v must go up. That's just a basic fact from looking at that formula. Similarly, if we keep r constant and we increase omega, then v must go up. So if you increase either of them, then the tangential speed is going to increase. So to be specific, if you double r, you're going to double v. If you halve r, you're going to halve v. If you double omega, you're going to double v. If you halve omega, you're going to halve v. So it's a very simple relationship between all of those properties. So back to centripetal acceleration. I promised we'd return to it, and here we are. We have the formula for centripetal acceleration as being v squared over r. I don't expect you to worry about where this comes from. If you're really interested, you can look up some stuff online, but all I want you to do is remember this formula. I don't generally like telling you just to remember something without me explaining it, but hopefully you can agree that it sort of makes sense. If you have a bigger acceleration, that radius is going to get smaller. Right? And if you divide something smaller on the right-hand side, you divide by something smaller, that makes your result bigger. So a smaller radius, bigger acceleration. So that's what we already expected. And conversely, if you think about the velocity, if you increase that velocity, while keeping the same acceleration, then your radius must get bigger because you're traveling further. Your magnitude is still staying constant, so you're traveling further. You got a bigger distance, so you must get a bigger radius. So hopefully you can agree that those relationships make sense. That if you increase the velocity, then your radius is going to increase. If you increase your acceleration, your radius is going to decrease. And then you can just remember this formula. So the centripetal acceleration is v squared over r. We put a little subscript c for centripetal. It's not required, but again, it's just a good habit to get into, to use those subscripts to remind yourself of what we're talking about and what we're dealing with. Centripetal force is the force that causes that centripetal acceleration, but we're still dealing with standard physics and Newton's second law still applies. So we just have F equals ma, but we're talking about centripetal force and centripetal acceleration. So Fc is equal to mac. That means we just have m times v squared over r. So the centripetal force needed to keep an object traveling in a circular path of radius r with velocity v, tangential speed v. And if the object has a mass m, then the force needed is mv squared over r. Just a little note that centripetal is the role of the force. It's not the type of force. So when we talked about the force due to gravity, the friction force, the push force, the friction, I just said friction, all the different forces, the normal force and tension force, spring force, all of those types of forces, they're a reference to what causes the force. Those are all a reference to what causes the force, whereas centripetal force, when we say centripetal, what we're talking about is the role of the force. That force will still be caused by one of those other mechanisms. It will be caused by friction or by tension or by gravity, but the centripetal is a description of the effect the force has on the object, and that is to make it travel in a circular path. So it's important to keep that in mind. Centripetal force still needs a cause. There still needs to be something causing that force, and part of our job often is to identify what that cause is. Just as an exercise, I'm not going to do this for you, but you can, if you want, go and check. I recommend you go and check that the units make sense. Do a bit of dimensional analysis or unit analysis on these two equations, that AC is equal to V squared over R. So A is an acceleration, we've got V squared over R on the right-hand side, and force is a force, and we've got mv squared over R on the right-hand side. So do check that the units come out correctly. It's a good exercise. Imagine that you've got something that is traveling in a circle, so it's experiencing a centripetal force, and then imagine that that centripetal force suddenly stops. What's going to happen? Well, that acceleration suddenly stops as well. Then the velocity will no longer change by Newton's second law. If you've got no net force, you've got no acceleration, and you've got constant velocity. Because we know that the speed at any point around the path is constant, we know what speed the object will have as soon as that force stops. And furthermore, we know that the direction of the object is always along the path. It's always tangent to the path. That's why we call it tangential speed, because we know that the velocity vector is always a tangent to the curve. So that tangential we don't need to include it when we talk about speed. Speed is fine just on its own, but tangential speed is just a reminder that we have the vector, if we're talking velocity, is going to be tangential to that circular path. So if that velocity is tangential to the circular path, then as soon as you let the object go, or the force for whatever reason stops, that object is just going to continue in a straight line from where it is along that tangent. So that's what happens. It's a common misconception, well, not misconception, but a lot of people haven't thought the problem through, and it's easy for people to imagine all sorts of different scenarios. A common one is that people think the object will just fly straight away from the center. So actually, I'll jump over to the document camera and I'll just illustrate a couple of common misunderstandings here. So one is that if you let an object go, so you've got an object that's traveling around the circle like this, you let it go here, a lot of people think that it's just going to go away from the center. Right? But of course, as I just said, at this point, this object has a velocity vector like that, tangential speed. So if you let it go here, then it's going to travel that way. And it'll go, just keep going in a straight line because there's no net force, there's no reason for that velocity vector to change. Another common one is that people sort of think it'll do the opposite, and that it might go curve off that way for some reason. Obviously that's not going to happen. It's not going to go straight out. So there are all sorts of different things that people think. Some people think that it might sort of have a bit of remaining tendency to go that way and it'll sort of go off that way. But again, that makes no sense because as soon as that force stops, there's nothing that can change the velocity vector. So whatever that velocity vector is right there, as soon as that force stops, it's stuck with that velocity vector. It cannot change. The last thing that I said we'd talk about for this sort of motion is centrifugal force. So imagine being in the system. The easiest one to imagine is a car driving around a perfect circle. So imagine that you're in a car and it's driving in a perfect circle at a constant speed. So that is just circular motion as we've defined it. It will feel like you are being pulled outwards. It'll feel like you're being pulled outwards away from the center of the circle. And that's because the car is pulling you inwards. It's that centripetal force that we talked about. In order for you to travel in a circle, your velocity has to be constantly changing directions, which means you have to be constantly accelerating towards the center of the circle, which means there has to be a constant force on you towards the center of the circle. And because you are being pulled towards the center, right, it feels like you are resisting that and it feels like you're actually being pulled outwards. And it's just this little confusion that our systems make, our bodies make, our brains make when we're in a rotating system. Remember, we don't generally go with rotating frames of reference. This is one of the reasons why. Sorry, we don't go with accelerating frames of reference. And this is a reason why rotating frames of reference are accelerating. As we just said, the direction is constantly changing. And we end up with these weird forces, these weird experiences. And it's because the car is pulling you towards the center, and your reaction force is obviously going to be the other way. So you feel like you're being pulled outwards away from the center. And in fact, that's one of the reasons that people think when you let an object go, it'll fly away from the center, because that's what it feels like. It feels like you're being pulled away from the center. But in reality, it's just that centripetal force that's being used to change your velocity direction. You still have velocity in the tangential direction, and that's the direction you would go if that centripetal force suddenly stopped. That feeling of being pulled outwards, even though you're actually being pulled inwards, is called centrifugal force. There's no reference frame that we'll deal with where you generally need to worry about it, aside from the thing I'm about to mention. But generally, we're not going to deal with centrifugal force. Some physicists even refer to it as a fictitious force because it's not really a real thing. It's our perception of a force that's being applied towards in the actual opposite direction to what it feels like. And the one thing that I will mention about centrifugal force, though, is that because it feels like we're being pulled outwards, it is one way that we can create artificial gravity on things like big sci-fi space stations. So this is one realistic artificial gravity. A lot of artificial gravity is complete nonsense and doesn't make any sense at all in terms of physics. But if you have a big ring or a donut type shape space station and it's rotating, then that means that it is applying a centrifugal force or a centripetal force to you, which feels like a centrifugal force. And that centrifugal force, if the ring is rotating fast enough, can feel just like gravity. You can actually set it to the same acceleration due to gravity, same force due to gravity, I should say. And so you can easily make artificial gravity using that kind of a setup. Technologically, we have the equipment, the ability to do something like this. We just haven't had the desire or need to yet. It's a lot of time and effort to build such a space station. The next part is going to talk about rotation of objects. So this is the idea of an object rotating about a fixed point. When discussing linear and circular motion, we treated the object as just a point. We said, here's a dot that represents our object, and it moves along this path. That was what we said. But in reality, the objects themselves are rotating as well. Consider a wheel on a bus that goes round and round. If the bus is traveling in a straight line, the wheel is undergoing linear motion, but it's also rotating. Right? It's undergoing linear motion. You could represent the wheel just as a dot, and that dot would just move along the road at a constant velocity if the bus is going at a constant velocity. But in reality, that wheel is actually rotating as well. It's not just traveling along at a constant velocity. So let's think about objects themselves rotating. A lot of what we just talked about for circular motion applies to rotational motion as well. So we have a center of rotation called the axis of rotation. That, in this case, is usually within, or it has to be within the object because it's a fixed rotation point. For a circular path, Here's the center, the object travels around it. This center point is not actually in the object is traveling around it. For rotation, if you've got a wheel that's rotating, the center, that axis of rotation, is inside the object. And that object is somehow secured at that position and allowed to rotate, but not allowed to move off that position. So the wheel cannot move off the axle of the bus, but the wheel can rotate about that axle. So we've got a center of rotation just as we did for center of circular paths. We've got the angle relative to some initial or fixed position. So again, just choose a point on your wheel and then define a direction as your initial position, and then measure the angle of that position, that spot you've chosen on the wheel, for example. So for example, on a bus wheel, you may, if they've got an air valve, I haven't looked at bus wheels, so I don't really know, but if it's got an air valve like a standard tire does, then you might use that as your reference point. And you might say, right, when that's perfectly vertically downwards, that's our rotation of 0 degrees. And by the time it gets to 90, it's up here. By the time it gets to 180, it's perfectly vertical, and so on. And so you can just measure that angle of rotation based on that initial starting point. We still have angular speed, omega, exactly the same. If we're defining our angle in some way, then our omega tells us how much that angle changes every second. And we still have the period exactly the same, the time taken to complete one full revolution about our axis. So very similar properties to what we saw for circular motion. But the tangential speed is not quite as straightforward. For example, we've got an animated GIF of a man spinning a colorful umbrella. What is the tangential speed of this umbrella? The question doesn't make any sense because different parts are traveling with different tangential speeds. The points right on the edge of the umbrella are traveling a lot faster. They have a much bigger path to go around. Every point along that, anywhere on that umbrella, you choose any point on that rainbow umbrella, and it has the same period because it does one full rotation in the same amount of time. But the distance from the very center of the umbrella will determine its tangential velocity. The furthest points out, remember that tangential speed was V equals R omega. If they've all got the same omega, they've all got the same angular speed because they've all got the same period, then the bigger the R, the bigger the tangential speed. So that point that's furthest from the center, those very tips of the umbrella, they've got the biggest R, they're going to have the biggest tangential speed. The points right in close to the axle, right close to the shaft of the umbrella, they have a tiny R, they're going to have tiny tangential speed. They've still got the exact same angular speed, but they've got very small linear speeds. Suppose the umbrella has a radius of 60 centimeters and is being twirled with a period of 1 second. So just to put some numbers to what I was just saying to reinforce this point that all the different parts of the umbrella will be traveling with different linear speeds. A point on the very edge of the umbrella has a path radius of 60 centimeters, so it's traveling a circle of 2 pi r equals 3.8 meters every second. So it has a tangential speed of 3.8 meters per second. But a point halfway from the center to the edge of the umbrella will have a path that is only path radius of only 30 centimeters, so a path length of only 1.9 meters, and therefore a linear speed of 1.9 meters per second. So you can see that the linear speed is different, even though they're both traveling with the exact same angular speed because they have the same period. Actually, before I move on to the next part, this is also what I mentioned about the child on the merry-go-round. The merry-go-round might have some specific angular velocity, and the child on the merry-go-round will have the same angular velocity, but it doesn't make sense to talk about the linear tangential speed of the child, of the merry-go-round itself, but it does for the child. The merry-go-round itself has different speeds depending on where you are on the merry-go-round, what point of the merry-go-round you look at. For that child, because they're in a fixed position away from the center of the merry-go-round, you can define that tangential speed for them very easily. The next part is torques. So far we've been talking about making things rotate, but we haven't really said how we cause that rotation. So a torque is any force that makes something rotate. So if we apply a force to make something move linearly, the result was dependent just on the direction. Right? We just said, right, here's a box, we're going to push it. We push it that way, so the box moves that way. Very simple. But if we apply a force to rotate something, now we have to keep track of where we push relative to that axis of rotation, relative to the point about which the object rotates. For example, this is just a wooden rod and it's fixed in the center, so it can spin about the center. If you push at the top, or we could imagine this is looking top down so that we don't have gravity to worry about. If you push at the top of our image, then it will rotate clockwise. But if you push at the bottom of our image, then it will rotate anti-clockwise. Those two forces could be identical. They are both the same magnitude, they are both the same direction, they're both being applied to our rotating rod, yet they cause different rotations. So now we not only have to think about the magnitude and direction of the force, but about where the force is being applied to the object. If you think about a door is a really good example for thinking about the effect that this location of your push has on the result of the push. If you push a door next to the handle, so the handle is normally the opposite side from the hinges for a very good reason. If you push a door there, then you'll get a nice swing of the door. But if you push halfway through the door, halfway across as per the middle diagram here, if you push halfway across with the exact same force, the door is not going to move as easily. Right? It's not going to swing as much. And if you push right next to the hinge, it's going to be very difficult, practically impossible to actually open that door by pushing here. So that force, even though it's not changing, is producing very different results based on its distance from the axis of rotation. All right? That distance from the axis of rotation has a specific name, and that is called the lever arm. The lever arm, we often use the symbol D. It's a distance, so we're in meters, and the dimension is L for a distance. The lever arm, though, can be a little bit complicated to figure out. If you are pushing perpendicular to your object, then generally the lever arm is just going to be the distance from the applied force. But technically, the lever arm is the distance, the shortest distance from the line of action of the applied force to the axis of rotation. So you can see in that second diagram, the line of action is just the force vector, but continued in both directions. Just make it into a big long line. And then the lever arm is the shortest possible distance from your axis to that line that you've just drawn. So that's all it is. It involves trigonometry to figure it out. Again, we're not really going to go into this too much in this course. I expect you to understand what the lever arm is, but I wouldn't worry too much about calculating it necessarily. I'm pretty sure there's nothing on the assignment about the lever arm, just about torques where they're perpendicular. So a torque is the name of that force that causes something to rotate, and it is just the product of the force and that lever arm, Fd. So torque is equal to Fd. The symbol is not a T, it's actually another Greek letter, tau. It looks like a curvy little T, so learn that little symbol. The units, force times distance, that's newtons times meters, so we've got Newton meters as our SI unit. And the dimensions, remember that the dimension of a force is newtons meters per second, which means I've done that wrong, kilograms meters per second. So I've done that dimension wrong. I think they should have another time -2, not -1. So the dimensions, mass, length squared, time to the -2. That is the dimensions of torque. Net torque, torques add just like forces, but now instead of remembering the direction of the force, we now have to think about I was about to say direction, but whether the torque is going to cause clockwise or anti-clockwise rotation. So generally our frame of reference for torques is simply going to be that one direction is positive and one is negative. So common is anti-clockwise is positive, clockwise is negative, but either way is perfectly acceptable. You can just choose one, call it positive, the other is negative, and then what you have to do is, again, do the physics. There's no strict rule. I'm not going to write out a set of rules for you to follow. If the force is going to make the object rotate counterclockwise, then you call that whatever you've defined it to be. If it's going to cause it to rotate clockwise, you call that the opposite, whatever you've defined that to be. So that's all torques are. You just add them like forces, and then the net torque will determine the overall resulting rotation of the object. Just as we had with forces, if there is no net torque, then we have no change in angular velocity. So torques change angular velocity just like forces change linear velocity. Right, so exact same idea. It's very sort of a parallel set of ideas. So if we've got a net zero torque, then we have no change in angular velocity, and the object will just keep rotating at whatever velocity it is rotating at. If you have a non-zero net torque, then we do have a change in velocity. So we're going to have a change in angular speed, I should say. That means we have to figure out how torques relate to changes in angular speed. That's beyond this course. We're not going to get into it. Essentially, if you get a problem and you find that you have a non-zero net torque, your conclusion would just be that this will change angular speed. We're not going to worry about how much or the properties of that. The last part of this lecture is on center of mass. So center of mass is a new concept, but we've actually kind of been talking about it already, as I'll point out. So the center of mass is just the average position of all the mass of an object. For a symmetrical object like a sphere or something that's geometrically simple like the cone pictured, it can be very easy to determine. In a sphere, it's going to be very center of the object. In a cone like this, like the one pictured, if that's a solid cone, then the center of mass would be right in the very center line, the axis, so right below that point, but only a quarter of h up from the base. That is where the center of mass would be for a cone. So it's the exact average position of all the mass in the object. In free body diagrams, when we represent objects as just dots, that's kind of what we've been doing. We've been putting a dot to represent the object, and that dot is essentially the center of mass of the object. When we draw a dot, we're not calling it the center of mass, but that's effectively what we are describing. When we apply forces, now that we care about where we apply the force, not just which direction, because torques depend on where you apply the force, gravity always acts at the center of mass. That's what gravity is. Gravity is an attraction between the mass of the Earth and the mass of the object, or the mass of whatever planet or star you're talking about, and the mass of the object. So that means that it's going to act at the average position of all of that mass, which is the center of mass. That's what the center of mass is. That's why it's useful. That is where gravity acts. For a force, if the line of action of the force goes through the center of mass, then it will not cause a torque. Right? It won't cause a torque because you're pushing directly in line with that center of mass. But if your force does not line up with the center of mass, that means you do have a lever arm. The line of action has some distance to your center of mass, and then it can cause a torque. It can cause the object to want to rotate about its center of mass. Rotation may result. I say may because it doesn't always result depending on the rest of the scenario. Center of masses can be a bit odd though. It's easy enough when you've got a solid object and the center of mass is in the middle of that solid object, but sometimes you have objects like a ring, that gold ring for example, where the center of mass is right in the center of the ring. There's no actual mass there. There's no ring there. The ring is a donut shape around that center of mass. So there's no actual ring at the center of mass, but that is where the center of mass is, and that is where gravity will effectively act on that ring. For something like that L-shaped block, the grey one below it, the center of mass could be inside the empty space in the corner inside that L shape. Even though, again, there's no actual mass there, there's no substance there, that is where the center of mass is. It's the average position. The average position isn't always inside the object itself. Since weight due to gravity is just the mass times the acceleration due to gravity, the center of gravity is actually the same as the center of mass. Right? That is, as I was just saying, the force due to gravity acts on that center of mass. So sometimes we'll call the center of mass the center of gravity, but that's only true when the object is being subjected to a gravitational force. Any object anywhere in the universe always has a center of mass. If it's got mass, it's got a center of mass, but it only has a center of gravity when it is being subjected to a gravitational force. So that's just a little clarification there. For that reason, I tend to stick with just talking about the center of mass and keep in mind that that is where gravity is going to act. In order to find the center of gravity, it's actually very simple. If you hang an object by any point, then the center of gravity or center of mass will always be directly below that point that you are holding it. That is just how it would, otherwise it would rotate, because you need the center of gravity to be perfectly downwards and the tension to be perfectly upwards in order for the system to be at rest, and they have to be acting along the same line of action, otherwise there would be a torque. So that means that that center of gravity, center of mass, has to be directly below the hanging point, the support point. That means if you go and hang it from two different points and draw your vertical line onto the object, then the point where those two lines cross will be the center of mass. So I'll just demonstrate that in the document camera. I'll get a new sheet of paper, that one's got a few things on it now. So if you have an object, I'm just going to make one up. You have an object and you hang it from this point, then it's going to rotate until the object is perfectly below it, and then you know that the center of mass is somewhere along this line. You don't know where yet, but you know it's somewhere along that line. And then you go and you change and you hang it by this point over here. And now it's going to spin around and it's going to end up hanging this way. Here's the string and it's going to hang that way. And then you know that the center of mass is somewhere along this line as well. If it's on this line and it's on this line, then it must be right here. I haven't drawn that very well because it looks more like it should be over here somewhere, but the idea is the same. The idea works for any object. If you hang it by two different points and just trace that vertical line downwards from each of those points once it's sitting still, that will be your center of mass where they cross over. So that is how to find the center of mass of any object. Stability, we're not going to talk in great detail. You can almost tune this out if you really want to, but it is nothing that isn't accessible to you at this point. The idea of stability is simply a statement that the center of mass has to be directly above some part of the base of the object that is making contact with whatever surface it is resting on. If it's not, then that means that you have unbalanced torques and the object will rotate. In the case on the left, the force pressing up from the surface it's on is across the whole base. It's pushing up everywhere, and the center of mass is right above part of that. So that means the forces are going to balance out. The torques can balance out easily, and that object is just going to sit there stable. In the case on the right, we would all expect that to fall over. And the reason it falls over is that the force that's being applied upwards can only be applied in the area of contact. And that means that it's going upwards, normal force, straight upwards. That means that it's going up and it's not going through the center of mass. Whereas gravity is acting at the center of mass and pulls that center of mass downwards. So that means you've got these unbalanced torques. Right? Center of gravity is pulling it down. Normal force is pointing up, but not through the center of mass. So it's causing a torque, which results in the object rotating, also known as falling over. So the reason we wanted to introduce that center of mass, so I've written this as a separate part, but really it's related to the center of mass, and it's the idea of free rotation. Any object that is set into free rotation, so that means you're rotating it but without a fixed axis. Remember, we had a fixed axis for our tire on an axle or a merry-go-round. They had fixed axes. Any object that is rotating freely will do so about its center of mass. You can visualize that, as I said, by, for example, throwing a ball. If you throw a ball and you give it a bit of spin as you throw it, it will rotate. As it travels, that rotation will be about its center of mass. So a good example of this is actually straight out of the textbook, although I've increased the visibility of those white dots for this lecture slide. The white dot represents the wrench's center of mass. As you can see, that center of mass just travels linearly because there's no net force acting on this object. You can imagine this being slid across a frictionless surface. So you're looking top down, sliding along a frictionless surface like an air hockey table or an ice rink or something. And as it does, it's rotating, but there's no net force acting on it. So it just slides along linearly in a straight line. So that center of mass is just undergoing linear translation, linear motion. So those white dots, straight line. You can see it's decelerating, so actually there is a net force, but the net force that it's experiencing is opposing the velocity because those white dots get closer together. So technically it is decelerating, but it's traveling in a straight line, so nice linear motion. However, while it's doing that, the wrench is rotating about its center of mass. And you can see that because we can observe where the handle is pointing. It's rotating, in this case, it's rotating clockwise about its center of mass as the center of mass is traveling to the right. In order to analyze motion like that, complex motion, you just do what I just did. You break it down into linear motion of the center of mass and then the rotation of the object about its own center of mass. So if you want to analyze a rugby ball that's spinning as it flies through the air, you look at the center of the mass of the ball and you analyze that just like you would any projectile. and then you look at the rotation of the ball and you analyze that as you would for any rotational object. So then you would end up with information about the path of the ball, and that would be all our standard projectile motion stuff. And then you would also have information about the rotation of the ball. So what is the angular speed? What is the tangential speed on the surface of the ball at different points? What's the center of rotation, which should be the center of mass because it's not fixed? What's the period, and all of that kind of information. So you'd end up with two different sets of data, two different sets of information about the same object. And you could then combine them to provide a model for that ball spinning as it travels. Right? So you would then use the same time, put it into each of the equations, and you'd be able to figure out exactly what that ball is doing at any point in time. So here's all the information. I guess I should actually just clarify that I don't expect you to be able to analyze complex motion like a rugby ball spinning through the air. My point is that you have the tools and the information to be able to do that. We're going to keep it a lot simpler in general than that, but you certainly have the information needed to undergo some basic, simple models of objects like that. So as usual, there's a review, all the information for you to double check. So do go through and look at all of that. But that effectively brings to an end our study of forces and simple motion. The last lesson for this section will actually look at pressure, which is related to force, but it's more about how that force is distributed across the surface. And then next section, so section 4, moves into talking about energy and work.